Today's lesson is going to be on data analysis. Data analysis is a pretty big piece of our measurement unit and introduction to physics. It's all about taking data, trying to interpret patterns and relationships and understanding data. And so we're going to go through several things here in this unit. And if you notice, I'm using a different program to record the video, so things might be a little bit different. I'm going to try to make this 15 minutes or less. So the topics we're going to discuss are rules of graphing, best fit line calculations and linear regression, interpolating and extrapolating, accuracy, percent error, precision, correlation coefficient, graphical relationships, and straightening the curve. Those are all the topics, hopefully, that I can cover in this 15 minutes. So first of all, why are graphs important? It's a simple visual way to represent data, and it's easier to see the patterns in the data when it's presented in picture form. So what we do is we take our data and we graph it, and we try to identify the relationship, and if we need to change how that data looks at all, we can change some of the variables in our x or y axis and straighten curves, and that's what we'll get to towards the end. And we can also write a mathematical equation to try to summarize the data and to try to put a rule so that we can understand what's going to happen with those two variables in the future. So let's just run through what our variables are called. We have the independent variable and the dependent variable. Hopefully these are familiar to you. The independent variable is the variable that's carefully controlled. Usually we put this on the x-axis and we carefully assign even increments. So time, for example, would be normally an independent variable. If we're going to measure the time it takes a runner to run a certain distance, we'll put that on the x-axis and we'll say maybe 1, 2, 3, 4, 5 seconds. The dependent variable is the variable that's measured. And so if we're trying to determine the distance that a runner runs, we're going to measure the distance in that specified time, and we plot that on the y-axis. So a dependent variable always depends on the independent variable. The independent variable is usually what you, the experimenter, purposely set up in advance. Alright, so here's some examples. Let's say a scientist records the temperature of an unknown solution every 30 seconds. Well, if we're recording temperature versus time, time would be the independent variable. So every 30 seconds we make a measurement of temperature. And so temperature would be the dependent variable, whereas time would be the independent variable. The force was measured as the mass was increased. Well, what did we measure? We measured force, so that's the dependent variable. The independent variable is what we purposely did as the experimenter. What did we do? We increased the mass. And it was probably a set amount that we increased the mass. Number 3, graph the population trend of the United States every year since 1980. Population should be the dependent variable, and time, or years, is the independent variable. And so that would be on the x-axis. Graph circumference as a function of diameter. Well, when we say something is graphed as a function of something else, diameter in this example would be on the x-axis, so that's the independent variable. Circumference would be on the y-axis, so that's the dependent variable. Number 5, purpose, to see what happens to acceleration as mass is increased. As we increase mass, so we purposely increase the mass and we see what happens to acceleration. So acceleration would be a dependent variable on the y-axis, and mass is an independent variable on the x-axis. So when we do a lab, when we collect data, we look at data, we have to graph the data, and when we graph it, there are specific rules that we have to follow to make a good graph. And I'm going to run through those rules with you. First of all, the graph should be neat, and we're going to use Excel or line paper to do this, and I'll show you in a later video how to use Excel to make graphs. But for now, you'll probably just make them on line paper, graph paper. make sure you have a title for your graph, and usually it's going to be just dependent variable versus independent variable. So if you're graphing distance and time, you would say distance versus time. It doesn't have to be anything fancy. Label the axes with the variable names. So if you're trying to graph distance and time, you should have distance written on the vertical axis, time written on the horizontal axis, and the units should be in parentheses. And we always measure our quantities in uh, SI quantities. So distance would be measured in meters, and time would be measured in seconds. So we shouldn't have measurements of miles or anything in there. And those should be in parentheses. Circle data points when graphing by hand. Normally when you put a data point down, you don't want it to be a big dot. You try to make a small dot so that it doesn't occupy a lot of space. A dot is supposed to be a dimensionless object. So you put a tiny little dot and then you put a circle around it just to denote that it's not a speck on the paper and it actually is a data point. And I'll show you an example of that in a second. Sketch or have a computer draw the best fit line on the graph. So when you do a best fit line, you want to use a ruler or a straight edge, and you want to make sure that the line crosses through the center of the data. And if you take a statistics class, you'll probably have some more in-depth instructions on making a best fit line, but in physics you just estimate where the center of the data is and you put a line through the middle of all those points. It's got to be straight though. Include the equation of the best fit line, and normally when you're doing this by hand you have to calculate the slope and then figure out where it crosses the y-axis. So you're going to write the equation in y equals mx plus b form, where m is the slope and b is the y-intercept. And last, include appropriate measures of accuracy, which is percent error, and the precision, which is the R value. And R value stands for correlation coefficient. We'll talk about that in a minute. It's a statistical number that relates to the precision of your data. In other words, it tells you how well the two variables actually correlate to each other. And normally you can't do that. You're not going to be calculating that by hand, but if you use Excel or your graphing calculator, you should be able to do the correlation coefficient on that. Alright, so here's an example that I've done by hand. I just put some sample data together and plotted the data on a graph, and you can see that on the x-axis here I have time, which is measured in hours, and on the vertical axis I have distance. It's kind of cut off there, and it's measured in kilometers. And notice that I've set this up so that I'm maximizing my graph space. I didn't make just a tiny little graph here in the corner. Instead, I purposely tried to stretch my x-axis and stretch my y-axis to utilize the entire graph space. I have a title at the top, and it's not a fancy title. I mean, I'm graphing distance and time, so I just say distance versus time. If I was graphing force and distance, it's simple, force versus distance. And I'm not trying to be fancy here. All I'm trying to do is show the quantities that I'm graphing. And notice the circles that I put around the data points. I put these circles here just to identify that they are data points and it's not a speck of, let's say, dust or something that dropped on the paper or something that the copier made, so that we can identify that those are points. Lastly, over on the right, I've calculated the slope, and using just 2 points on the graph, you can calculate the slope by doing the difference in y values divided by the difference in x values. Once you get the slope and the y-intercept, you can write an equation, which I have not done that, but I did calculate the slope. Notice too that the points that I picked to go into this equation were points on the line. They're not points that I plotted. They're data points that are actually on my line. And they're points that are pretty far away from each other. I purposely picked this point because this is where the line crossed the grid lines on my graph, and I could tell exactly where that point sat on the graph. and I chose that point because it was towards the top of the graph. And then I chose another point here way towards the bottom, and I purposely picked that point as well because it was a point that sat on the line and on the grid lines. And so I was able to write down the value of that point more accurately. And when you get points that are spaced farther apart, you're able to minimize your error. If I pick 2 points that are very close together, my error is going to be larger. And so that's just something you learn along the way. To pick points on the line that are far apart, that makes your slope more accurate. Alright, so what is a best fit line? A best fit line is actually a line or curve that best describes the data. So when I drew that line that went through the data points there, I purposely put a line through the center of the data to describe the trend in the data. Also, the statistical process of calculating the best fit line is called linear regression. And you can do linear regression on your calculator or in Excel. And this process is something that statisticians do all the time, and we do in physics as well, to come up with relationships in data. In order to do a linear regression on your calculator, there's a few things that you would have to do, and I'm not going to have time in this video, I realize, because I'm already running pretty close to my 15 minutes. But you have to input data into the calculator, and you can actually run a program in your calculator to calculate that. Now, I'll make a separate video on using the calculator to find linear regressions. A couple other things in terms of vocabulary that we should know is related to, oh, seems like my graph didn't print on that one. Interpolating versus extrapolating. To interpolate means to estimate between data points, and to extrapolate means to estimate beyond the data points. So when we have a line, if the line shows an upward trend, we can estimate where that line is going to go beyond our data. We call that extrapolating. When we estimate between data points, we know that there must be other data points in between, maybe that we just have not collected yet. That's called interpolating. So we can interpolate or extrapolate based on our line in our linear regression once we've written that line down on a graph. Some other vocab words, some terms that I'm going to be using a lot for error analysis are accuracy versus precision. Accuracy describes how well the results agree with the true value. If you're trying to determine, let's say, the acceleration of gravity, you already know that the acceleration of gravity is 9.8. That's the true value. And let's say you do your lab and you come up with an answer of 9.7. Is that pretty good? Well, they're only different by 0.1. So the percent error, if you conducted the percent error, you would find that, yeah, that's a pretty good measurement for the acceleration rate of gravity. However, if you had, let's say, the actual number for whatever lab you were trying to do was 2, and you came up with an answer of 1, is that pretty good? It's not. Well, you're only off by 1, but you're actually off by 100%. Your percent error is 100% because you're only half as big as the number you wanted. So percent error gives us an idea of how accurate our results are compared to the true value. Precision is a measure of the degree of variability or reliability or replication. And we use precision to try to explain the relationship between two variables. And that's written down as the correlation coefficient. And so if you're using Excel or your calculator, you'll come up with an R value. And the better the R value, the more precise your data is. If you get an R value that's very close to 1 or -1, that's great. If you get an R value that's close to 0, that's not great. Think of it as a percent. And if you get an R value of 0.9, that's 90% precise. So you're doing awesome.